a quiet region of space, a star begins as a cool cloud of gas and dust. Gravity slowly draws the particles closer together. The cloud becomes denser over many thousands of years. As it contracts, the center grows warmer. This early stage is called a molecular cloud. Most of the material is hydrogen, the simplest element. The cloud drifts in darkness, changing almost too slowly to notice. As gravity continues its steady pull, the cloud fragments into smaller clumps. Each clump may become a new star. The center of a clump grows hotter as atoms move more quickly. Pressure builds gently. When the core becomes dense enough, it forms a protostar. The young object is still wrapped in dust. It glows faintly from the heat of contraction, not yet from nuclear fusion. Inside the protostar, temperature and pressure keep rising. Hydrogen atoms begin to move with enough energy to overcome their natural repulsion. When they fuse together, they form helium. This process releases energy in the form of light and heat. The outward pressure from fusion balances gravity. The star enters a long, steady phase called the main sequence. During the main sequence, a star spends most of its life. Hydrogen in the core slowly turns into helium. The balance between gravity pulling inward and energy pushing outward remains stable. The star shines steadily for millions or even billions of years. Its surface temperature and color depend on its mass. Smaller stars glow red and cool. Larger stars appear hotter and more blue. A star like the Sun changes very gradually. As hydrogen in the core becomes scarce, fusion slows in that central region. Gravity begins to compress the core again. The outer layers respond by expanding outward. The star becomes larger and cooler at the surface. This stage is known as a red giant. The change unfolds over vast stretches of time. In the red giant phase, the core contracts and heats further. Hydrogen fusion may continue in a shell around the core. Eventually, temperatures become high enough for helium to fuse into heavier elements such as carbon and oxygen. The outer layers drift farther away. The star grows luminous but less dense at its edges. Its internal structure becomes more layered and complex. For stars with modest mass, the outer layers are gently released into space. Gas flows outward in a slow wind. This material forms a glowing cloud called a planetary nebula. The exposed core remains behind. Without outer layers pressing inward, fusion ceases. The remaining core cools over time. It becomes a white dwarf, small and dense. A white dwarf no longer produces energy through fusion. It shines from stored heat, radiating it slowly into space. The object is about the size of a planet, yet it contains much of the original star's mass. This matter is tightly packed. Over billions of years, it cools and fades. It gradually becomes darker and less active. Stars much more massive than the Sun follow a different path. Their greater mass creates higher pressures in the core. They burn through hydrogen more quickly. After leaving the main sequence, they expand into red supergiants. In their cores, fusion continues with heavier elements. Each stage of fusion produces less energy than the one before. As heavier elements form, the core becomes layered like an onion. Hydrogen, helium, carbon, and other elements fuse in shells. The process continues until iron forms in the center. Iron does not release energy through fusion. When the core fills with iron, it can no longer support itself through fusion pressure. Gravity begins to dominate. The core of a massive star collapses in a fraction of a second. Protons and electrons combine to form neutrons. The collapse halts when neutron pressure resists further compression. The outer layers rebound and move outward. This event is called a supernova. It releases elements into space, enriching nearby clouds with material for future stars. After the supernova, the remaining core may become a neutron star. This object is extremely dense. A small sphere can contain more mass than the Sun. Neutron stars often spin rapidly. Some emit beams of radiation from their magnetic poles. When these beams sweep past Earth, they are observed as pulses. These objects are known as pulsars. If the original star was very massive, even neutron pressure cannot stop the collapse. Gravity compresses the core further. It forms a black hole, a region where gravity is so strong that light cannot escape. The boundary around it is called the event horizon. Matter that crosses this boundary becomes part of the black hole. Throughout these stages, gravity acts as the guiding force. It gathers material to form stars. It shapes their internal balance. It determines how they end. The mass of a star at birth influences each later phase. Small differences in mass lead to very different outcomes. Yet the underlying physical laws remain consistent across the universe. The elements created inside stars do not remain isolated. When stars shed their outer layers or explode, they return material to space. This gas and dust mix with existing clouds. New generations of stars form from this enriched material. Planets may arise around them. The atoms in living organisms were once forged in stellar cores. Time moves slowly in the life of a star. Human lifespans are brief by comparison. A star's steady glow may last longer than civilizations. Even its final stages unfold over spans that exceed written history. Observing distant stars allows astronomers to see different phases at once, because light takes time to travel. Astronomers study starlight to understand these processes. By spreading light into a spectrum, they identify elements present in a star. The color and brightness reveal temperature and size. Careful measurements of motion show how stars form in clusters. Observations across many wavelengths provide a fuller picture of stellar evolution. Star clusters offer a calm record of shared origins. The stars within a cluster formed from the same cloud. They differ mainly in mass. By comparing their brightness and color, scientists trace how stars of different masses age. This method confirms predictions made by models of nuclear fusion and gravity. In distant galaxies, countless stars follow similar patterns. Some are young and blue, shining brightly. Others are older and red, nearing later stages. Galaxies slowly change as generations of stars form and fade. The quiet cycle of birth, fusion, expansion, and release continues across cosmic time. Within this vast setting, each star follows a path shaped by mass and governed by simple forces. Hydrogen gathers, fusion begins, and light emerges. Layers shift as fuel changes. Matter returns to space in time. New clouds assemble under gravity's steady influence, beginning the process again in silence. A star is a large sphere of hot gas held together by gravity. Most of its mass is hydrogen, the simplest and most abundant element in the universe. Gravity pulls the gas inward, while pressure from heat pushes outward. When these forces balance, the star remains stable. Its light comes from energy released deep in its core through nuclear fusion. At the center of a star, temperatures reach millions of degrees. Under such heat and pressure, hydrogen nuclei move fast enough to combine. This process is called nuclear fusion. When hydrogen fuses into helium, a small amount of mass becomes energy. That energy travels outward and eventually escapes as light. The steady glow we see is the result of this ongoing reaction. Although stars appear small in the night sky, they are vast in size. Our sun is an average star, yet it could contain more than 1 million Earths by volume. Other stars are smaller and cooler, while some are much larger and hotter. Distance makes them appear as points of light. Their true scale is difficult to imagine from Earth. A star does not burn like wood or fuel in a fire. Burning is a chemical reaction that uses oxygen. A star's energy comes from nuclear reactions instead. These reactions change one element into another. The energy released is far greater than that of chemical burning. This difference allows stars to shine steadily for millions or billions of years. Gravity is essential to the existence of a star. Without gravity, the hot gas would drift apart into space. Gravity compresses the gas toward the center. As it compresses, the temperature rises. This heat enables fusion to begin. The balance between gravity pulling inward and fusion pushing outward defines what makes a star stable. Stars form from clouds of gas and dust in space. When a region within a cloud becomes dense enough, gravity causes it to collapse. As the material falls inward, it heats up. If the central temperature becomes high enough, fusion starts. At that moment, a new star is born. It begins its long period of steady shining. The color of a star tells us about its surface temperature. Cooler stars appear red or orange. Hotter stars glow white or blue. This color difference is linked to how much energy leaves the surface. Temperature also relates to mass. More massive stars tend to be hotter and brighter, while smaller stars are cooler and dimmer. A star is made mostly of plasma, a state of matter similar to gas but with charged particles. In plasma, electrons are not bound tightly to atoms. This allows the material to respond to magnetic fields. Inside a star, plasma moves slowly in currents. These motions can create magnetic activity on the surface. The light from a star carries information. When spread into a spectrum, it shows dark lines at specific wavelengths. These lines reveal which elements are present. Hydrogen is almost always dominant, but other elements appear in smaller amounts. By studying these patterns, scientists learn about a star's composition and physical conditions. Stars vary greatly in mass. Some contain only a fraction of the sun's mass. Others are many times more massive. Mass influences how bright a star shines and how long it will live. A massive star uses its fuel quickly. A smaller star consumes hydrogen more slowly. This difference shapes the length and character of its life. A star's surface is called the photosphere. This is the layer from which most visible light escapes. Above it lie thinner layers of hot gas. The surface may show darker regions known as star spots, caused by magnetic activity. These spots are cooler than surrounding areas, though still very hot by earthly standards. Energy created in a star's core does not reach the surface instantly. It moves outward through layers of dense plasma. In some regions, energy travels by radiation. In others, it is carried by convection, where hot material rises and cooler material sinks. This journey from core to surface can take many thousands of years. Stars are not evenly scattered through space. They often form in groups known as clusters. In these groups, stars share a common origin in the same cloud of gas. Over time, gravity may slowly separate them. Yet their similar age and composition reveal that they began together in a quiet region of space. Many stars have planets orbiting them. These planetary systems form from disks of gas and dust around young stars. As material in the disk clumps together, planets take shape. The star's gravity keeps them in orbit. In this way, a star can become the center of a small system, providing light and heat to nearby worlds. Some stars appear to change brightness over time. These are called variable stars. The changes may occur because the star expands and contracts slightly. In other cases, a companion star may pass in front and block some light. Observing these patterns helps astronomers measure distances and understand stellar behavior. A star's brightness depends on both its energy output and its distance from us. A nearby dim star may appear brighter than a distant luminous one. To compare stars fairly, astronomers calculate intrinsic brightness. This reveals how much energy a star truly emits, independent of how far away it is. Binary stars are systems where two stars orbit a common center. They are common in our galaxy. The motion of each star reveals the presence of the other. By studying their orbits, scientists can measure stellar mass with precision. These systems provide valuable insight into how stars form and evolve. The Sun is the closest example of a star. Its light supports life on Earth. By studying the Sun, scientists gain detailed knowledge about stellar processes. Observations of solar flares, sunspots, and radiation help refine models. These models can then be applied to distant stars, which cannot be observed as closely. Stars shine across a wide range of wavelengths, not only visible light. They emit infrared, ultraviolet, and other forms of radiation. Each range reveals different layers and processes. Instruments designed for specific wavelengths provide a fuller understanding of stellar structure and activity. In simple terms, a star is a self-luminous sphere of plasma powered by nuclear fusion. Gravity shapes its form, and fusion sustains its light. Its mass determines its temperature, color, and lifespan. Though distant and silent, each star follows clear physical laws. Their steady glow marks the presence of ongoing energy deep within. A stellar nursery is a vast cloud of gas and dust where new stars begin to form. These regions are often cold and dense compared to the surrounding space. Most of the material is hydrogen, with small amounts of helium and heavier elements. Gravity gently draws parts of the cloud inward. Over time, denser pockets emerge within the quiet darkness. Inside these clouds, temperatures can be only a few degrees above absolute zero. The cold allows atoms to remain bound in simple molecules. Dust grains drift between the gas particles. Though the cloud seems calm, gravity is always at work. Small variations in density slowly grow. A slightly denser region attracts more material and becomes heavier. As matter gathers, a clump within the cloud begins to contract. The contraction is gradual and can last hundreds of thousands of years. With increasing density, the center grows warmer. The growing warmth marks the earliest step towards star formation. At this stage, the object is still hidden within layers of dust that block visible light. Stellar nurseries are often found in spiral arms of galaxies. These regions contain large amounts of gas, providing raw material for new stars. The clouds can stretch across many light years. Within them, clusters of stars may form at roughly the same time. Each star emerges from a separate pocket of collapsing gas. Radiation from nearby young stars can influence a nursery. Their light and stellar winds gently push against surrounding gas. This pressure may compress nearby regions, encouraging further collapse. In this way, star formation can move through a cloud in stages. One generation of stars quietly shapes the conditions for the next. The dust within stellar nurseries plays an important role. Though it makes up only a small fraction of the mass, it absorbs and scatters light. This creates dark lanes visible against brighter backgrounds. Dust also helps cool the cloud by radiating heat away. Cooling allows gravity to overcome internal pressure more easily. As a clump contracts further, it forms a rotating disk of material around a central core. Conservation of angular momentum causes the spin to increase slightly as the cloud shrinks. The central region grows denser and hotter. Surrounding material flattens into a disk. This disk may later give rise to planets. Infrared observations are useful for studying stellar nurseries. Visible light cannot easily pass through dense dust. Infrared radiation, with longer wavelengths, can penetrate these regions more effectively. Telescopes sensitive to infrared light reveal hidden protostars and warm structures inside the cloud. Within a nursery, many protostars may exist at different stages. Some are just beginning to collapse. Others are close to igniting nuclear fusion. The environment is not uniform. Density, temperature, and motion vary from place to place. This variety leads to stars with different masses and characteristics. Magnetic fields thread through stellar nurseries. Though weak, they influence the motion of charged particles in the plasma. Magnetic forces can slow the collapse of certain regions. They also guide flows of gas and shape filament-like structures within the cloud. These effects contribute to the overall pattern of star formation. Turbulence within the cloud creates gentle motions in the gas. These motions can compress material in some areas and disperse it in others. Turbulence arises from earlier stellar activity, galactic motion, or nearby events. It adds complexity to the process, yet gravity remains the primary force guiding collapse. Some stellar nurseries are visible as emission nebulae. In these regions, young massive stars emit ultraviolet light that energizes nearby hydrogen gas. The gas then glows softly in characteristic colors. This glow outlines the structure of the cloud. It also marks areas where recent star formation has taken place. Other nurseries appear as dark nebulae. These clouds block light from stars behind them, creating silhouettes against the sky. Though they seem empty, they are rich with material. Inside, protostars may be forming quietly. Their early light is hidden by thick layers of dust and gas. The scale of a stellar nursery is difficult to grasp. A single cloud can span dozens or even hundreds of light years. Within that expanse, thousands of stars may eventually form. Yet the process is not hurried. It unfolds gradually, shaped by gravity, pressure, and the cooling effects of radiation. Star formation is not perfectly efficient. Only a portion of the cloud's mass becomes part of stars. The rest may remain as gas or be dispersed by stellar winds and radiation. Over time, the nursery thins. The bright young stars it created may drift apart, leaving the original cloud altered. In dense regions, stars often form in clusters. These clusters can remain bound by gravity for long periods. Because the stars share a common origin, they have similar ages and compositions. Studying such clusters helps astronomers understand how conditions in the nursery influence stellar properties. Jets of material sometimes emerge from young protostars. These narrow streams move outward along the star's rotational axis. They help carry away excess angular momentum. By reducing spin, jets allow more material to fall inward. This supports continued growth of the central forming star. Chemical reactions occur within the cold gas of a nursery. Simple molecules such as carbon monoxide and water can form on dust grains. These molecules emit radiation at specific wavelengths. Observing this radiation provides insight into the cloud's temperature, density, and motion. Over millions of years, a stellar nursery gradually changes. As more stars ignite, their radiation reshapes the remaining cloud. Gas is heated, compressed, or dispersed. The once dark region becomes more transparent. What began as a quiet cloud transforms into a field of young stars. Stellar nurseries are part of a continuous cycle in galaxies. Gas enriched by older stars gathers into new clouds. Within these clouds, gravity begins its steady work again. New stars emerge from material shaped by earlier generations. The process repeats calmly across cosmic time. Gravity is a fundamental force that draws matter together. Every particle with mass attracts every other particle. In everyday life, this pull seems gentle, yet across vast distances it shapes galaxies and stars. Within a cloud of gas and dust, gravity works quietly. If the cloud is dense enough, its own weight begins to pull it inward, starting a gradual collapse. In a large molecular cloud, tiny variations in density are always present. A slightly denser region has a bit more gravity. This extra pull gathers more material from its surroundings. As mass increases, the gravitational force strengthens. The process feeds on itself. Over time, a stable cloud can become unstable, and collapse begins in a focused region. As a cloud contracts, gravitational potential energy is converted into heat. Particles move faster as they fall inward. The temperature at the center rises slowly but steadily. This warming creates internal pressure that resists further collapse. Whether the cloud continues shrinking depends on the balance between gravity pulling inward and pressure pushing outward. A key concept in collapse is the gene's mass. This value describes the minimum mass a region must have for gravity to overcome internal pressure. If a cloud fragment exceeds this threshold, collapse is likely. If it is below that limit, pressure can keep it stable. Temperature and density both influence this delicate balance. Cooling plays an important role in allowing collapse to continue. As gas radiates heat into space, its internal pressure decreases. Lower pressure makes it easier for gravity to compress the material further. Dust grains and simple molecules help radiate energy away. In this way, cooling supports the steady inward motion of matter. During collapse, the cloud does not shrink evenly. Denser clumps form within the larger structure. Each clump may collapse independently, leading to the formation of multiple stars. This fragmentation explains why stars often form in clusters. Gravity shapes each fragment according to its mass and local conditions. Rotation affects how collapse unfolds. Even a small initial spin becomes more noticeable as the cloud contracts. Conservation of angular momentum causes rotation to increase as size decreases. This growing spin can prevent material from falling directly inward. Instead, gas settles into a rotating disk around a central core. Magnetic fields can slow gravitational collapse. Charged particles in the cloud interact with magnetic lines of force. These fields resist compression to some degree. Over time, processes such as ambipolar diffusion allow neutral particles to slip past magnetic influences. Gradually, gravity gains the upper hand and contraction continues. Turbulent motion within a cloud adds complexity to collapse. Turbulence can both support and compress regions of gas. In some places, it creates temporary pressure that counters gravity. In others, it pushes material together, encouraging denser pockets to form. Despite these motions, gravity remains the persistent force guiding long-term change. As collapse proceeds, the central density increases dramatically. The inner region becomes opaque to its own radiation. Heat is trapped more effectively, raising the temperature further. This stage leads toward the formation of a protostar. The outer layers continue to fall inward, feeding mass into the growing center. The timescale of gravitational collapse depends on density. Denser regions collapse more quickly than diffuse ones. Astronomers estimate this timescale using the freefall time, which describes how long a cloud would take to collapse without pressure support. In reality, pressure and rotation lengthen this process. Gravity does not weaken with distance in a simple way inside a cloud. Each particle feels the combined pull of surrounding mass. As matter gathers toward the center, the gravitational field becomes stronger there. This concentration accelerates infall, increasing both density and temperature in the core. In the early universe, gravity shaped the first structures. Slight variations in matter distribution grew over time. Regions with more mass attracted additional material. Gradually, these areas formed the seeds of galaxies and stars. The same principle of gravitational growth operates on many different scales. External forces can trigger collapse in a stable cloud. A passing shock wave from a nearby supernova may compress the gas. This added pressure can push a region beyond the threshold where gravity dominates. Once collapse begins, it can proceed even after the external influence has faded. As material falls inward, it often follows curved paths rather than straight lines. Interactions between particles and magnetic fields guide the flow. Streams of gas may spiral toward the center. These motions contribute to the formation of disks and jets around young stellar objects. Gravity acts universally and continuously. It does not require contact between objects. Even in the near vacuum of space, its influence extends across light years. Though weak compared to other forces at small scales, its cumulative effect over large masses makes it the architect of cosmic structure. When collapse reaches sufficient temperature and pressure in the core, nuclear fusion can begin. At that point, the inward pull of gravity is balanced by outward energy from fusion. The long phase of stellar stability begins. Gravity, which initiated collapse, now helps maintain equilibrium. Not all collapsing regions form stars. If a fragment loses mass or gains heat, pressure may halt contraction. The cloud can re-expand or disperse. In other cases, collapse may produce objects too small for sustained fusion. These become brown dwarfs, shaped by gravity but lacking steady nuclear burning. Over time, gravitational collapse transforms diffuse gas into dense, luminous objects. The change is gradual and governed by measurable laws. By observing clouds at different stages, astronomers trace this progression. Careful study confirms that gravity, acting quietly and persistently, guides the journey from cloud to star. Across the universe, gravity continues its steady influence. It gathers matter, shapes collapse, and sets the stage for new light. Though invisible, its effects are evident in every star and galaxy. The calm inward pull, balanced by pressure and motion, forms the foundation of stellar birth. Nuclear fusion is the process that powers stars. It occurs when light atomic nuclei combine to form a heavier nucleus. In the cores of stars, temperatures and pressures are extremely high. Under these conditions, hydrogen nuclei move fast enough to come very close together. When they fuse, a small amount of mass is converted into energy. The energy released in fusion comes from a change in mass. According to the relation described by Einstein, mass and energy are connected. When hydrogen nuclei merge into helium, the resulting helium nucleus has slightly less mass than the original parts. The missing mass appears as energy. This energy supports the star against gravity. In stars like the Sun, fusion begins with hydrogen. The most common pathway is called the proton-proton chain. In this sequence, hydrogen nuclei combine through several steps to form helium. Each step releases energy in the form of light and neutrinos. The overall process is steady and can continue for billions of years. More massive stars often rely on a different pathway known as the CNO cycle. In this cycle, carbon, nitrogen, and oxygen act as catalysts. They help convert hydrogen into helium more efficiently at higher temperatures. Although the steps differ, the result is the same. Hydrogen is transformed, and energy is released. Fusion requires nuclei to overcome their natural electrical repulsion. Positively charged protons repel each other. Only at very high temperatures do they move fast enough to approach closely. At extremely small distances, the strong nuclear force binds them together. This force acts only over short ranges but is very powerful. Pressure in a star's core plays a key role in maintaining fusion. Gravity compresses the gas, raising both temperature and density. Higher density increases the chance that nuclei will collide. Without sufficient pressure, fusion would slow or stop. The balance between gravity and fusion keeps the star stable. The energy from fusion does not escape instantly. Photons created in the core are absorbed and re-emitted many times. This slow journey through dense layers can take thousands or even millions of years. By the time energy reaches the surface, it emerges as visible light and other forms of radiation. As hydrogen in the core becomes depleted, fusion changes. In stars of suitable mass, helium can begin to fuse into heavier elements. Helium nuclei combine to form carbon and oxygen. This stage requires even higher temperatures. It occurs later in a star's life, after core hydrogen is largely used up. Each stage of fusion produces elements that can serve as fuel for later reactions, if conditions allow. In very massive stars, fusion continues beyond helium. Carbon, neon, oxygen, and silicon can fuse in successive stages. Each stage occurs at higher temperature and lasts for a shorter time. Fusion reactions release energy because lighter elements have lower binding energy per nucleon than certain heavier ones. Up to iron, fusion generally releases energy. Beyond iron, fusion requires energy instead of producing it. This limit plays an important role in determining how massive stars end their lives. Neutrinos are nearly massless particles produced during fusion. They interact very weakly with matter. Because of this, they escape from a star's core almost immediately, detecting neutrinos from. The Sun confirms that fusion is actively occurring at its center, even though the core itself cannot be seen. The rate of fusion depends strongly on temperature. A small increase in core temperature can cause a significant rise in fusion rate. This sensitivity helps regulate a star's structure. If fusion increases too much, the star expands slightly, cooling the core. If fusion slows, gravity compresses the core, raising temperature again. In brown dwarfs, conditions are not hot enough to sustain steady hydrogen fusion. Some may briefly fuse deuterium, a heavier form of hydrogen. However, they lack the mass needed for long-term fusion. This distinction separates true stars from substellar objects shaped mainly by gravity. Fusion in stars differs from processes in nuclear reactors on Earth. Stellar fusion occurs naturally under immense pressure and temperature. On Earth, scientists attempt to replicate these conditions in controlled experiments. The goal is to harness fusion as a clean energy source, though it remains technically challenging. The energy produced by fusion supports life on Earth. Light from the Sun warms the planet and drives weather patterns. Plants convert sunlight into chemical energy through photosynthesis. In this indirect way, nuclear fusion in the sun sustains ecosystems and influences climate. Over time, fusion changes a star's internal composition. The core gradually fills with helium as hydrogen is consumed. This shift alters the balance of pressure and gravity. Structural adjustments follow, guiding the star into new phases of evolution. Fusion thus shapes both energy output and long-term development. Fusion reactions occur in plasma, where electrons and nuclei move freely. The high temperature keeps atoms ionized. In this state, particles can collide frequently. Plasma behavior is influenced by magnetic fields and pressure. Understanding plasma physics helps scientists model how fusion proceeds in stellar cores. In small, cool stars, fusion proceeds slowly. Their lower core temperatures mean reactions occur at a reduced rate. As a result, these stars can shine for very long periods, sometimes trillions of years. Their gentle fusion provides a stable output of energy over extended timescales. In very massive stars, fusion progresses rapidly. High core temperatures accelerate nuclear reactions. These stars burn through their fuel in a relatively short time. Though brief compared to smaller stars, their fusion creates many heavier elements that later enrich the surrounding space. Nuclear fusion is a quiet but powerful process. It transforms simple hydrogen into more complex elements. Through this transformation, mass becomes energy and light fills space. The steady rhythm of fusion in countless stars shapes the chemical and energetic structure of the universe. A main sequence star is one that is steadily fusing hydrogen into helium in its core. This stage represents the longest and most stable period in a star's life. During this time, gravity pulling inward is balanced by pressure from nuclear fusion pushing outward. The star's size and brightness remain relatively constant over millions or billions of years. The position of a star on the main sequence depends mostly on its mass. More massive stars are hotter and brighter. Less massive stars are cooler and dimmer. When plotted on a Hertzsprung-Russell diagram, main sequence stars form a broad diagonal band. This pattern reflects the link between temperature, luminosity, and mass. In the core of a main sequence star, hydrogen nuclei combine through nuclear fusion. In stars similar to the Sun, the proton-proton chain dominates. In more massive stars, the CNO cycle becomes more important. Both processes convert hydrogen into helium and release energy. This energy maintains internal pressure. The Sun is a typical example of a main sequence star. It has been in this stable phase for about 4.6 billion years. Scientists estimate it will remain on the main sequence for roughly 5 billion more. During this period, its energy output changes only gradually, allowing stable conditions in its surrounding system. Main sequence stars vary widely in size. Red dwarfs are small and cool, with masses much lower than the Sun. Blue main sequence stars are larger and far hotter. Despite these differences, they share the same basic structure. Each maintains equilibrium through the steady fusion of hydrogen in its core. The surface temperature of a main sequence star influences its color. Cooler stars appear red or orange. Medium temperature stars appear yellow or white. Hotter stars glow blue-white. These colors arise from the distribution of light emitted at different wavelengths, determined by surface temperature. A star's lifetime on the main sequence is closely tied to its mass. Massive stars consume hydrogen quickly because their high core temperatures increase fusion rates. Smaller stars burn fuel more slowly. As a result, red dwarfs can remain on the main sequence for extremely long periods. Inside a main sequence star, energy moves outward from the core. In some regions, it travels mainly by radiation. In others, it moves through convection, where hot material rises and cooler material sinks. The balance between these processes depends on mass and internal temperature. As hydrogen gradually converts to helium, the composition of the core changes. Helium accumulates in the center because it does not fuse at the same temperature as hydrogen. Over time, this buildup alters pressure and density conditions. The star slowly adjusts its structure to maintain balance. Main sequence stars are often found in clusters. In open clusters, many stars share a common age and origin. Because mass determines how quickly a star evolves, more massive members leave the main sequence first. Studying clusters helps astronomers confirm models of stellar evolution. The brightness of a main sequence star can be described by its luminosity. Luminosity depends strongly on mass. A star only slightly more massive than the Sun may be much more luminous. This relationship shows how sensitive fusion rates are to core temperature and pressure. Magnetic activity is common in many main sequence stars. In stars with convective outer layers, magnetic fields can become twisted and concentrated. This can produce star spots, flares, and variations in brightness. Such activity is linked to the motion of plasma within the star. Rotation also plays a role in main sequence behavior. Young stars often rotate more quickly. Over time, stellar winds can carry away angular momentum, slowing rotation. The rate of spin can influence magnetic field strength and surface activity patterns. Red dwarf main sequence stars are especially numerous in the galaxy. Though faint and small, they make up the majority of stars by number. Their low mass means slow hydrogen fusion. Because of this efficiency, they can shine steadily for times far longer than the current age of the universe. More massive main sequence stars shine brightly but live briefly. Their intense energy output results from rapid fusion in the core. Although they contribute greatly to the light of young star clusters, their main sequence phase may last only millions of years. The internal structure of a main sequence star is shaped by hydrostatic equilibrium. Gravity compresses inward, while gas pressure and radiation push outward. This balance keeps the star from collapsing or expanding dramatically. Small changes in fusion rate are corrected through slight adjustments in size and temperature. As a main sequence star ages, its core temperature gradually rises. The buildup of helium increases core density. To maintain pressure balance, the star's fusion rate increases slightly. This causes a slow rise in luminosity over time, even while the star remains in the same general phase. The stability of the main sequence allows planetary systems to develop around many stars. A steady energy output over long periods provides consistent radiation. This stability is considered important for the long-term evolution of environments on orbiting planets. Eventually, hydrogen in the core becomes too scarce to sustain fusion at the same rate. When this happens, the balance between gravity and pressure shifts. The core contracts, and the star prepares to enter a new stage. The long calm of the main sequence begins to change. Main sequence stars represent a quiet balance in stellar evolution. They convert hydrogen into helium with steady rhythm. Their mass defines their temperature, brightness, and lifespan. Though varied in appearance, they share the same internal principle of equilibrium maintained by fusion and gravity. A red giant is a star that has exhausted most of the hydrogen in its core. Without sufficient hydrogen fusion at the center, gravity causes the core to contract. As the core shrinks, it becomes hotter. This heat ignites hydrogen fusion in a surrounding shell. The outer layers expand and cool, giving the star a reddish appearance. The expansion of a red giant is gradual but extensive. A star like the Sun may grow many times its original diameter. Although the surface becomes cooler, the overall luminosity often increases. The larger surface area radiates more total energy. Despite its size, the outer layers are less dense than during the main sequence phase. Inside a red giant, the structure becomes layered. A dense core of helium lies at the center. Around it, hydrogen continues to fuse in a thin shell. The energy from this shell pushes outward. This outward pressure causes the star's envelope to swell. The balance between gravity and pressure shifts compared to earlier stages. The reddish color of a red giant results from its lower surface temperature. As the star expands, its outer layers cool to temperatures around 3,000 to 5,000 degrees Celsius. Cooler temperatures shift the peak of emitted light toward longer wavelengths. This produces an orange or red hue when observed from a distance. As the helium core contracts, its temperature continues to rise. In stars of sufficient mass, conditions eventually allow helium fusion to begin. Helium nuclei combine to form carbon and oxygen. This process releases energy and briefly stabilizes the core. The transition marks an important step in the star's evolution. For stars similar in mass to the Sun, helium fusion can begin suddenly in an event known as a helium flash. Although the term suggests intensity, it occurs deep within the core and is not visible externally. After this adjustment, the star settles into a more stable phase of helium burning. Red giants often experience increased mass loss. Their outer layers are loosely bound and can drift into space as a slow stellar wind. Over time, this process removes significant material. The released gas contributes to the surrounding interstellar medium, enriching it with heavier elements formed inside the star. The outer envelope of a red giant is convective. Hot material rises toward the surface, cools, and then sinks again. This motion can create variations in brightness. Some red giants are classified as variable stars because their light output changes slightly over regular periods. The future of a red giant depends largely on its initial mass. Stars with modest mass will not reach temperatures high enough to fuse elements heavier than helium. Their evolution will eventually lead to the shedding of outer layers, leaving behind a dense core. More massive stars follow a different path. As a red giant expands, it may engulf nearby planets. In our own solar system, the Sun is expected to expand far enough to affect the inner planets. The timeline for this transformation spans billions of years. The gradual nature of the change reflects the steady pace of stellar evolution. Red giants are common in older star clusters. In such clusters, the more massive stars have already left the main sequence. Observing the number and distribution of red giants helps astronomers estimate the age of the cluster. Their presence marks a later stage in stellar development. The density contrast within a red giant is striking. The core is extremely dense and hot, while the outer layers are extended and diffuse. This difference arises because gravity compresses the core more strongly once hydrogen is depleted. The outer layers respond by expanding outward. In some red giants, pulsations occur as the star expands and contracts slightly. These changes are linked to variations in internal pressure and opacity. The pulsations can alter brightness over weeks or months. Such behavior provides insight into the internal structure of the star. Chemical elements produced during earlier fusion stages can be brought to the surface of a red giant. Convection carries material from deep layers upward. Spectral analysis may reveal enhanced amounts of carbon or other elements. This mixing process contributes to chemical enrichment of the galaxy. The luminosity of a red giant can be many hundreds or thousands of times that of the Sun. Despite this brightness, the surface temperature remains relatively low. The combination of high luminosity and cool temperature is a defining feature of this stage on the Hertzsprung-Russell diagram. In binary systems, a red giant may transfer mass to a nearby companion star. If the companion is compact, such as a white dwarf, the transferred material can lead to complex interactions. These systems provide valuable data for understanding stellar mass exchange and evolution. The timescale of the red giant phase is shorter than the main sequence stage. Once core hydrogen is depleted, changes occur more rapidly. Even so, the transformation unfolds over millions of years. The process remains gradual on human timescales. Observations of red giants in different galaxies show similar patterns. The physical principles governing expansion, fusion, and mass loss are consistent throughout the universe. This universality supports current models of stellar structure and evolution. In its red giant stage, a star reflects both its past and its future. The helium core records the long period of hydrogen fusion. The expanding envelope signals change. The star adjusts to new internal conditions, guided by gravity and nuclear processes. Red giants represent a transitional phase in stellar life. The steady balance of the main sequence gives way to expansion and internal restructuring. Though larger and cooler at the surface, the star continues to evolve quietly, preparing for the next chapter shaped by its mass and composition. A supernova is the final stage in the life of certain massive stars. It occurs when the core can no longer support itself against gravity. For very massive stars, fusion builds heavier elements up to iron. Iron does not release energy through fusion. Without outward pressure from fusion, the core collapses under its own weight. During core collapse, the central region contracts rapidly. Electrons and protons combine to form neutrons and neutrinos. The core becomes extremely dense in a short time. When nuclear forces resist further compression, the collapse halts. The outer layers fall inward, then rebound outward in response to the sudden resistance. The outward-moving material forms the visible supernova explosion. Although the term suggests intensity, the process follows clear physical laws. Energy released from the collapse and neutrino interactions drives the outer layers away from the core. The star briefly becomes far brighter than usual before gradually fading over weeks or months. Supernovae are important sources of heavy elements. During the explosion, conditions allow elements heavier than iron to form. These elements are created through rapid neutron capture processes. When the outer layers disperse, they carry these newly formed elements into surrounding space. Not all supernovae arise from massive stars. In binary systems, a white dwarf can accrete matter from a companion. If it gains enough mass to approach a critical limit, internal pressure and temperature increase. Carbon fusion can ignite throughout the star in a runaway reaction, leading to a different type of supernova. This second type is known as a type Ia supernova. Unlike core collapse events, it does not leave behind a dense remnant. The white dwarf is disrupted entirely. Because these explosions have consistent peak brightness, astronomers use them to measure cosmic distances with precision. Core collapse supernovae leave behind compact remnants. If the remaining core mass is moderate, it becomes a neutron star. If it is greater, gravity continues compressing the core into a black hole. The exact outcome depends on the original mass of the star and details of the collapse. Neutrinos play a significant role during core collapse. Vast numbers are produced as the core contracts. Most escape into space with little interaction. However, a small fraction transfers energy to the surrounding layers, helping power the outward motion of the explosion. The light from a supernova does not come solely from the initial blast. As radioactive elements formed during the explosion decay, they release additional energy. This decay contributes to the brightness observed over time. The gradual fading follows predictable patterns linked to these processes. Supernova remnants are expanding clouds of gas and dust. Over thousands of years, the material spreads into surrounding space. Shock waves from the explosion can compress nearby gas clouds. This compression may encourage new regions of star formation in the affected areas. The structure of a massive star before collapse is layered. Different elements fuse in shells around the core. This layered arrangement influences how the explosion unfolds. The composition of each shell affects the types of elements ejected into space. Although supernovae are rare in a single galaxy, their cumulative effect is significant. Over cosmic time, many such events have occurred. They enrich the interstellar medium with elements necessary for planets and life. Without these explosions, heavier elements would be far less abundant. Astronomers detect supernovae by monitoring changes in brightness across galaxies. When a new bright point appears where none was seen before, careful measurements follow. Spectral analysis reveals the type of explosion and the elements present in the expanding material. The energy released in a supernova is immense compared to ordinary stellar output. Yet most of it is carried away by neutrinos rather than visible light. The visible brightness is only a small fraction of the total energy involved in the collapse. In the case of core collapse supernovae, the transition from stable fusion to collapse happens quickly on stellar timescales. Once the iron core reaches a critical mass, no further fusion can provide support. Gravity completes the process in a matter of seconds. Supernova observations have helped refine models of stellar evolution. By comparing theoretical predictions with light curves and spectra, scientists test their understanding of nuclear physics and gravitational dynamics under extreme conditions. The expanding debris from a supernova interacts with surrounding gas. As it moves outward, it slows and cools. Over time, the remnant becomes less distinct. The material eventually blends into the broader interstellar medium, contributing to future generations of stars. In some cases, the collapsing core forms a rapidly spinning neutron star with strong magnetic fields. These objects may emit regular pulses of radiation. Their existence confirms the extreme densities reached during supernova core collapse. Supernovae also influence the structure of galaxies. The energy they release can heat surrounding gas and regulate star formation rates. In this way, individual stellar deaths contribute to large-scale galactic evolution. A supernova marks the end of one stellar life but the beginning of new cycles. The dispersed elements mix with interstellar clouds. From these enriched regions, new stars and planetary systems may form. The process continues, shaped by gravity and nuclear forces across time. A white dwarf is the dense remnant left behind when a star of modest mass completes its red giant phase. After shedding its outer layers into space, the remaining core is exposed. This core no longer supports nuclear fusion. It shines because of residual heat stored during earlier stages. Over time, it slowly cools and fades. White dwarfs are small compared to ordinary stars. Many are similar in size to Earth, yet they contain a mass comparable to that of the Sun. This means their matter is extremely dense. A small amount of white dwarf material would weigh far more than the same volume on Earth. The stability of a white dwarf comes from electron degeneracy pressure. In this state, electrons are packed closely together. Quantum mechanical principles prevent them from occupying the same energy state. This creates a pressure that does not depend on temperature. It supports the star against further gravitational collapse. Unlike main sequence stars, white dwarfs do not generate energy through fusion. Their light comes from stored thermal energy. As they radiate this heat into space, their temperature gradually decreases. The cooling process can take billions of years, making white dwarfs long-lasting stellar remnants. Most white dwarfs are composed mainly of carbon and oxygen. These elements formed during earlier stages of helium fusion in the star's core. Because fusion has ended, no new elements are created. The composition reflects the star's final active phase before collapse into a compact remnant. There is a limit to how massive a white dwarf can be. This boundary, known as the Chandrasekhar limit, is about 1.4 times the mass of the Sun. If a white dwarf approaches this mass, electron degeneracy pressure can no longer support it. Further collapse or explosive reactions may occur. The surface of a white dwarf can be very hot when it first forms. Temperatures may exceed 100,000 degrees Celsius. Despite this heat, its small size limits total brightness. As cooling continues, the surface temperature declines. The star becomes less luminous over long spans of time. White dwarfs often reside at the center of planetary nebulae. The glowing gas around them is material expelled during the red giant phase. Ultraviolet radiation from the hot white dwarf excites this gas, causing it to emit light. Over time, the nebula disperses, leaving the white dwarf alone. In binary systems, white dwarfs can interact with companion stars. If material flows from the companion onto the white dwarf, it can accumulate on the surface. Under certain conditions, this may lead to periodic outbursts known as novae. These events brighten the system temporarily. A white dwarf's density is so high that a teaspoon of its material would have enormous mass. This density arises because gravity has compressed matter to an extreme degree. At these conditions, atoms are stripped of electrons, forming a compact plasma supported by quantum pressure. White dwarfs follow a predictable cooling path. Astronomers study their temperature and luminosity to estimate their age. In star clusters, the distribution of white dwarf temperatures helps determine how long ago the cluster formed. Their cooling acts as a natural clock. Over vast periods, a white dwarf will continue to cool and dim. In theory, it could eventually become a black dwarf, a cold and dark remnant. However, the universe is not old enough for any black dwarfs to exist yet. All known white dwarfs still retain some warmth. The gravity at the surface of a white dwarf is intense. An object dropped there would accelerate rapidly. This strong gravity also affects light leaving the surface, causing a slight gravitational redshift. Such effects have been measured and confirm theoretical predictions. White dwarfs no longer undergo internal convection driven by fusion. Their structure is relatively stable. Heat gradually moves outward from the interior. The absence of active nuclear reactions marks the end of the star's energy-producing life. Some white dwarfs possess strong magnetic fields. These fields can influence the motion of charged particles near the surface. In certain binary systems, magnetic white dwarfs channel incoming material along field lines, creating localized hotspots. The formation of a white dwarf is not violent in itself. The star loses its outer layers gently through stellar winds. What remains contracts until electron degeneracy pressure halts further collapse. The process is governed by gradual changes rather than sudden disruption. White dwarfs are common in our galaxy. Many stars with masses similar to the Sun will eventually become white dwarfs. Over billions of years, they accumulate as silent remnants of earlier generations of stars. The light from a white dwarf can reveal details about its composition. Spectral lines show whether hydrogen or helium dominates the outer atmosphere. These thin atmospheric layers affect how the star radiates heat into space. Although small and faint, white dwarfs are important to understanding stellar evolution. They represent the final stage for most stars. By studying them, astronomers trace the life cycles of stars that once shone more brightly. A white dwarf is a quiet endpoint shaped by gravity and quantum physics. It contains the compressed memory of a star's past fusion. Slowly radiating away stored heat, it remains as a dense, steady presence in the vastness of space. A neutron star forms when the core of a massive star collapses after a supernova. Gravity compresses the core so strongly that protons and electrons combine into neutrons. The result is an object of extraordinary density. Though only about 20 kilometers across, it can contain more mass than the Sun. The matter inside a neutron star is packed tightly together. Most of it consists of neutrons in a highly compressed state. This dense material is supported by neutron degeneracy pressure and nuclear forces. These forces resist further collapse, balancing the intense inward pull of gravity. The surface gravity of a neutron star is extremely strong. An object released above the surface would accelerate rapidly. Light leaving the surface is affected by gravity, causing measurable shifts in wavelength. These effects confirm predictions from general relativity under extreme conditions. Neutron stars often rotate very quickly. When the original star collapses, conservation of angular momentum increases its spin. Some neutron stars rotate many times per second. This rapid rotation can remain stable for long periods, gradually slowing as energy is lost. Many neutron stars have strong magnetic fields. These fields can be trillions of times stronger than Earth's. Charged particles moving along magnetic field lines emit radiation. If this radiation is directed toward Earth as the star rotates, it is observed as regular pulses. Such rotating neutron stars are known as pulsars. The pulses occur with remarkable precision. By measuring their timing, astronomers study the structure of space, test gravitational theories, and detect subtle cosmic phenomena. The interior structure of a neutron star is layered. Beneath a thin crust of nuclei lies a region of superfluid neutrons. Deeper still, matter may exist in exotic states not found elsewhere. The exact composition remains an active area of research. Neutron stars cool over time by emitting radiation and neutrinos. Shortly after formation, they are extremely hot. As energy escapes, their temperature declines gradually. Even after cooling, they remain detectable through X-ray or radio emissions. In binary systems, neutron stars can interact with companion stars. Matter drawn from the companion may form an accretion disk. As this material falls inward, it heats and emits X-rays. These systems are studied as X-ray binaries. If two neutron stars orbit each other closely, they may gradually spiral together. Gravitational waves carry energy away from the system. When they merge, they can produce detectable ripples in spacetime and create heavy elements such as gold and platinum. The density of a neutron star is difficult to imagine. A small sample of its material would weigh billions of tons on Earth. This density results from gravity compressing matter beyond ordinary atomic structure. Despite their small size, neutron stars influence their surroundings. Their strong gravity affects nearby matter and light. Their magnetic fields shape particle motion in space. These influences can extend far beyond the star itself. Some neutron stars exhibit sudden changes in rotation called glitches. These events are thought to arise from shifts in the superfluid interior. Observing such changes provides insight into the physics of matter at extreme densities. Neutron stars are born from stars initially much more massive than the Sun. Only stars within a certain mass range leave neutron stars behind. If the core mass is too high, collapse continues into a black hole instead. The study of neutron stars bridges astrophysics and nuclear physics. Conditions within them cannot be replicated on Earth. Observations help scientists refine models of matter under intense pressure and density. Neutron stars emit radiation across different wavelengths. Radio waves, X-rays, and sometimes gamma rays are detected. Each wavelength reveals different processes near the surface or in surrounding material. The magnetic axis of a neutron star is often misaligned with its rotation axis. This misalignment causes the beam of radiation to sweep through space. If Earth lies in its path, the beam is observed as a pulse. Over very long timescales, neutron stars lose rotational energy. As they slow, their emitted radiation weakens. Some may become difficult to detect, remaining as quiet remnants of earlier stellar activity. In certain conditions, matter on a neutron star's surface can undergo sudden nuclear reactions. These reactions produce brief increases in X-ray brightness known as bursts. They occur when accumulated material ignites under pressure. Neutron stars represent one possible outcome of stellar evolution. They are compact, dense, and governed by gravity and quantum principles. Though small in size, they reveal much about the behavior of matter and energy in extreme environments. The Sun is a typical main sequence star located at the center of our solar system. It formed about 4.6 billion years ago from a collapsing cloud of gas and dust. Most of its mass is hydrogen, with helium as the second most abundant element. Through nuclear fusion in its core, it steadily converts hydrogen into helium, releasing energy that radiates outward. At the core of the Sun, temperatures reach around 15 million degrees Celsius. Under these conditions, hydrogen nuclei fuse through the proton-proton chain reaction. This process produces helium, neutrinos, and energy. The outward pressure from this energy balances the inward pull of gravity, maintaining a stable structure. The sun's energy travels outward from the core through different layers. In the radiative zone, energy moves mainly by radiation, with photons being absorbed and re-emitted many times. In the outer convective zone, hot plasma rises and cooler plasma sinks. This slow circulation helps carry energy to the surface. The visible surface of the sun is called the photosphere. It has a temperature of about 5,500 degrees Celsius. From this layer, light escapes into space and reaches Earth after about 8 minutes. The photosphere appears bright and textured due to convection patterns known as granulation. Above the photosphere lie the chromosphere and the corona. The chromosphere is a thin layer visible during solar eclipses. The corona extends far into space and is much hotter than the surface. Its high temperature is linked to magnetic activity and plasma interactions. Sunspots are cooler regions on the photosphere caused by intense magnetic fields. These fields reduce convection in localized areas, lowering surface temperature slightly. Sunspots often appear in pairs or groups and vary in number over an approximately 11-year cycle. The sun rotates, but not as a solid body. Because it is made of plasma, its equator rotates faster than its poles. This differential rotation contributes to twisting and strengthening magnetic fields. These magnetic processes influence solar activity. Solar flares are sudden releases of energy linked to magnetic field changes. They emit radiation across the electromagnetic spectrum. While most solar activity has little effect on Earth, strong events can influence satellites and communication systems. The solar wind is a steady stream of charged particles flowing outward from the corona. This wind fills the solar system and interacts with planetary magnetic fields. When it reaches Earth, it can produce auroras near the poles. The sun's mass makes up more than 99% of the total mass of the solar system. Its gravity keeps planets, asteroids, and comets in orbit. Without this central gravitational force, the solar system would not remain bound together. Over time, the sun's core composition changes. Helium gradually accumulates as hydrogen is fused. This buildup causes a slow increase in core temperature and luminosity. The sun becomes slightly brighter as it ages, though changes are gradual. The sun is about halfway through its main sequence lifetime. It is expected to remain stable for roughly another 5 billion years. After that, it will expand into a red giant, altering conditions in the inner solar system. Solar neutrinos are produced in the core during fusion. These nearly massless particles travel outward almost unimpeded. Detecting them on Earth confirms that fusion is occurring at the sun's center as predicted by theory. The sun's light provides energy for life on Earth. Through photosynthesis, plants convert sunlight into chemical energy. This energy supports food chains and influences climate and weather patterns. Spectral analysis of sunlight reveals dark absorption lines. These lines correspond to specific elements in the sun's outer layers. Hydrogen and helium dominate, but traces of heavier elements are also present. The sun's magnetic field reverses polarity approximately every 11 years. This reversal is part of the solar cycle. The number of sunspots and level of activity rise and fall during this cycle. Although the sun appears constant to human perception, it is dynamic on many scales. Plasma flows, magnetic interactions, and radiation processes occur continuously. These processes follow well-understood physical laws. The study of the sun, known as heliophysics, helps scientists understand other stars. Because it is close, detailed observations are possible. These insights are applied to more distant stars throughout the galaxy. As a star, the sun is neither unusually large nor unusually small. It represents a common type of star in the Milky Way. Its properties provide a useful reference point for understanding stellar structure. The sun's steady fusion, balanced by gravity, defines its present state. It radiates energy into space with quiet consistency. In doing so, it serves as a nearby example of how stars function throughout the universe. The slow death of a star begins when hydrogen in its core becomes scarce. For most of its life, fusion of hydrogen into helium provides steady outward pressure. As this fuel is depleted, the balance between pressure and gravity changes. The core contracts under its own weight, and the outer layers respond by expanding outward. In stars similar to the Sun, this transition leads to the red giant phase. The core grows denser and hotter while hydrogen fusion continues in a surrounding shell. The outer atmosphere expands and cools. Although the star becomes larger and more luminous, the changes unfold gradually over millions of years. As contraction continues, temperatures in the core may become high enough for helium fusion. Helium nuclei combine to form carbon and oxygen. This stage provides temporary stability. Yet helium fuel is limited, and once it is used, the core cannot sustain further fusion at the same rate. For low and intermediate mass stars, fusion does not proceed beyond carbon and oxygen. When helium burning ends, the core contracts again. The outer layers become loosely bound and drift into space through steady stellar winds. This gentle mass loss marks a quiet transformation rather than a sudden event. The expanding shell of gas forms what is known as a planetary nebula. Ultraviolet radiation from the exposed core illuminates the drifting material. Over time, the gas disperses into the surrounding interstellar medium. The core remains behind as a compact white dwarf. The white dwarf no longer generates energy through fusion. It shines only because of stored thermal energy. With no new source of heat, it gradually cools. This cooling process takes billions of years. The star's death is not abrupt, but a long fading into darkness. In smaller stars, such as red dwarfs, the process is even slower. Their low mass allows hydrogen to be consumed at a very gradual rate. Some may burn for trillions of years. The universe is not yet old enough for any red dwarf to have completed its life cycle. More massive stars follow a different path. After helium fusion, they can fuse heavier elements in successive stages. Each stage occurs more quickly than the last. Eventually, iron accumulates in the core. Iron fusion does not release energy, and the star can no longer maintain equilibrium. When fusion ceases in a massive star's core, gravity takes over. The core collapses and the outer layers may be expelled in a supernova. Though the explosion is brief, the lead-up involves a long sequence of gradual changes in the star's interior. If the remaining core mass is moderate, it becomes a neutron star. If it is greater, collapse continues into a black hole. These outcomes depend on the star's original mass. Each represents a different form of stellar remnant shaped by gravity. In binary systems, the slow death of one star can influence its companion. Material transferred between stars can alter their evolution. In some cases, a white dwarf may gain enough mass to trigger further reactions, complicating the final stages. The chemical elements produced during a star's life are released into space as it dies. Carbon, oxygen, and other heavier elements mix with interstellar gas. These materials become part of new clouds that may form future stars and planets. Over time, star clusters reveal patterns of stellar aging. The most massive stars evolve first, leaving the main sequence early. Less massive stars follow more slowly. Observing clusters allows astronomers to trace different stages of stellar decline. The luminosity of a dying star often changes gradually. As internal structure shifts, brightness can increase or decrease. Pulsations may occur in some late-stage stars. These variations reflect adjustments in pressure and temperature. The slow death of a star is governed by predictable physical principles. Gravity, nuclear fusion, and thermodynamics guide each phase. Although the timescales are vast, the sequence follows a consistent pattern based on mass and composition. As a white dwarf cools, it becomes fainter and redder. In theory, after immense spans of time, it would become a cold black dwarf. However, such objects do not yet exist, as the universe is still relatively young compared to these timescales. The remnants of massive stars, such as neutron stars, also evolve slowly. They cool and may lose rotational energy over time. Though their birth may involve dramatic change, their long-term evolution is gradual. Across galaxies, countless stars are in different stages of decline. Some are just leaving the main sequence. Others are expanding into giants. Many have already become compact remnants. This variety reflects the ongoing passage of cosmic time. The slow death of stars does not signal an end to activity. Instead, it redistributes matter and energy. The elements forged within stars return to space, contributing to new structures. In this steady cycle, stars are born, shine, and gradually transform. Their deaths are not abrupt conclusions but extended transitions. Through slow cooling or structural change, each star yields its material back to the universe.